Alright, this is my presentation on Blackjack for CSE-120, Section 50. I'm Alex Minnic, and due date for this is 7/20/2026, July 20th. So, let's get into it. So, introduction. This program is meant to emulate the casino game Blackjack in the Python code language. The card, deck, and hand classes shown in the code screenshots coming represent a comprehensive simulation of a live casino blackjack table round. Its primary purpose is to model the progression of individual player hands, card generation arrays, value calculations, and outcome contingencies such as dealer busts, natural blackjacks, also known as natural 21s, or player turnovers on down cards. This presentation presents a detailed examination of the program's code's strategic goals, program mechanics, structure, and logic flows. Additionally, it addresses the conceptual design challenges faced during its creation, the timeline and development tracking, and the intermediate programming concepts that came up throughout this project's development. Going on to the goal of the code. At its core, the Python Blackjack program aims to accurately recreate the complete mathematical and tactical flow of a standard casino table game. In blackjack gambling, a player competes directly against a house dealer, in most cases a casino, starting with a base hand of 2 cards, with the overarching goal of maximizing their combined face value of up to a hard threshold of 21 points without exceeding it. The code mirrors this system by tracking the changing state of card objects inside active hands. On each turn, the user inputs a strategic play, either requesting a hit to draw a card or declaring a stand to lock in their hand. And the program recalculates and evaluates the underlying data attributes. One of the most important goals of this simulation is logical clarity and operational transparency. The program uses explicit print statements to convey status updates after every single player decision. If a user draws an ace, the game logic automatically evaluates the overall score to choose between an 11 or 1 valuation. If the score exceeds 21 points, the simulation will then detect a bust. This halts the execution and updates the state variables to give the victory to the house. It's assuming the player busts. Likewise, if the dealer fails to reach a hard total of 17, an automated control loop makes the house draw cards until the legal rule limits are satisfied. So now we'll move on into the structure of the code. So first one we have is the class definition block, or the core blueprint for an individual card. So this section introduces the base card class, which acts as a foundational data packet for the entire simulation. The class encapsulates 2 instance attributes, suit and rank. By converting textual strings to an instantiated object, the code ensures that every card detail dealt retains its physical identity throughout runtime memory blocks. The special dunder method _str_ is overridden and to automatically provide a human-readable format whenever the application prints a hand to the screen, or the output screen, I should say. And then we'll go on number 2. What we have here is the card value property, dynamic value mapping evaluation. So this segment establishes a read-only property decorator named value inside the card object. It uses conditional logic to translate rank representations such as string integers or royalty titles like king or queen or jack, so on, into numerical game points. Face cards are caught by a list/membership expression and assigned a flat value of 10 points, while standardized numbers are cast directly to machine integers via the int function. Aces are all initialized at a maximum weight of 11 points, creating a logical entry state that the downstream hand calculation matrices can easily parse. Number 3. Nope, let's go back there. Hot shot. Okay. Number 3. Class definition block, the 52 card deck assembly. The deck serves as a collection manager for a group of 52 independent card objects. Its initialization method uses a nested list to multiply the 4 legal suits across the 13 available card ranks, populating a list storage named self.cards. Once generation is complete, the constructor calls its shuffle routine, passing the collection array through Python's random.shuffle algorithm to guarantee random card distributions across subsequent dealings. Now we go on to 4. There we are. Card dealing routine, or mutating the deck stack. This method provides an extraction getaway. This method shown here provides an extraction getaway that transfers the card instances from the master deck list into the player's hand. It acts as a standard stack mechanism, executing the .pop operation to delete the top card element from memory while also reducing the remaining deck size. To prevent stack overflow crashes, the conditional boundary check verifies that the array's length is greater than 0 before performing the removal, throwing an error if a dealing action is attempted on an empty set. Now we go to number 5. Class definition block, the player and dealer hand logic. The hand class acts as a localized ledger that tracks the current point holdings for both human operators and the machine dealer. Upon instantiation, its constructor defines an empty array designated as self.cards. The companion method add_card accepts incoming card objects from the deck and appends them directly onto the hand's tracking index, overriding the _str. Underscore method joins the string representations of all currently held card objects into a clear sequence for output. Number 5 is done. We're on to number 6, because that comes after 5. Hand value calculation and ace adjustment logic, or dynamic scoring matrix. So this block of code represents one of the most important logic sections in the code. It computes total hand scores while finishing the variable nature of ace points. It first aggregates the default maximum. Aggregates the default maximum values of all elements via a generator expression. Next, a secondary counter tracks the frequency of ace cards inside the array. A state tracking loop checks if the accumulated total exceeds the hard loss threshold of 21. If it does, and an ace is present, the program subtracts 10 points from the total and drops the active ace tracker by 1. This loop runs continuously until the hand either falls under 21 or runs out of aces. Now we go on to number 7. Game state display routine, or managing the virtual casino felt. Felt like a table. Also, anyway, the display underscore game underscore state routine serves as the visual rendering engine for the command line user interface. So for the user input, it handles asymmetric information management by accepting a Boolean flag named hide underscore dealer underscore card. When set to true, it references index 0 of the dealer hand while masking subsequent array entries behind a hidden card label. When changed to false during the showdown phase, it clears the masking layer to display the dealer's full hand and complete calculation scores to the player. Showing them to the player, I should say. So now we're on number 8. Main gameplay loop setup and initial deal. Setting up the rounds. The main driving routine, play underscore blackjack, serves as the central organizing framework for each round of play. It begins by spawning an initialized deck and allocating 2 distinct hand objects into memory stack allocations. It then executes a deterministic loop that runs twice, calling the deck's dealing engine to distribute cards across the board. Once this phase is complete, it triggers the board to display the board display to outline the parameters of the current match conditions. So it says, hey, this is what's happening. This is what's happening on the board. Now we go to number 9, which is the next thing. We have player action decision loop and handling the hit stand interface. So this block manages user input validation and execution loops. The system prompts the operator for a character flag and uses string transformations .strip.upper to neutralize casing issues or white spaces. If the user chooses a hit command, a new card is drawn and the interface updates, and a conditional check verifies if the hand value exceeds 21. If the score is too high, the program prints a loss statement and exits. Simple enough? Not really. On number 10, automated dealer turn. executing the soft 17 stand threshold. Once the human player locks in their score by standing, control shifts to the automated dealer code. The system sets the display mask flag to false to reveal the house's hidden holdings. It then starts an evaluation loop that reads the dealer's score array against a fixed casino threshold value of 17. The house acts deterministically. If its current score remains strictly below 17, it will continue hitting and drawing cards, printing out updates upon the loop termination criteria until the loop termination criteria are satisfied. All right, to number 11, we're almost there. So, win determination and outcome analysis matrix, resolving the board state, as I called it. This final relational evaluation code, processes all surviving board scores to resolve payouts and figure out the winner. It uses an if-else matrix to look for outcomes in a specific priority order, first checking if the house busted, then verifying the player's final point value, then verifying if the player's final point value beats the dealer's score, and finally assessing if the dealer's hand is better. If none of these parameters are triggered, the script defaults to an end state code that handles a draw outcome, printing push. So push is equal to like a draw or a tie. And then finally, on number 12 for how the structure of the code is. Replay loop driver and managing persistent multi-round execution. So this initialization code manages the persistent layer of the console application by checking Python's global namespace variable _name_. It ensures the game only starts when executed deliberately. It wraps the entire game inside a continuous loop, granting the user of the program an endless session where they can complete a round, look over their results, and immediately start a fresh game without having to manually restart the code. And now we get to go to the timeline. How long did this thing take me? Quite a while. So the developmental life of this code can be divided into 3 phases: initial design and planning, code development, and testing/refining. The initial design phase took roughly 3.5 hours, excluding breaks, and including sketching charts, defining state structures, and figuring out how user input choices would interact with the deck arrays. So the active coding phase required several hours of deployment, pushing close to 4 hours a week. Me being deployed, I should say, to PyCharm. Totaling 12 hours through the 3 weeks I had budgeted in my project proposal. Initial work involved building the card blueprints, defining deck generation arrays, and writing hand accumulation methods. The value calculation method required particular attention because it must handle complex changing card conditions across varied states. One of the biggest challenges was keeping the correct order of operations. For instance, the hand's ace counter must aggregate totals across the entire array before checking if a point drop is needed. This specifically was the hardest part of the entire code development. Close of it was like making sure everything is nested so you could keep it going. But anyway, finally, testing the program required numerous revisions, changes, and rewrites. Test runs included runs that purposely triggered double ace drops, player busts, dealer soft 17 stands, and score ties, or tied scores, or draws, however you want to say it. Code adjustments were made when unexpected behaviors appeared, such as a lowercase h letter crashing the inputs or early calculations failing to clear a hidden card score. This testing stage took a lot longer than I thought it would, totaling around 7 hours of work for this testing. So totaling everything together, we're at 23 hours-ish, because got the 12, 7, 3.5. But I didn't include breaks in that. So just raw, me and PyCharm, just clacking away. Anyway. All right, on to new concepts introduced. So while this program uses Python basics, it also introduces many intermediate object-oriented programming concepts. Object-oriented abstraction is the main structural concept encountered. Each distinct hand retains its own localized memory stack and state attributes, allowing the code to scale into multiplayer setups or multi-deck configurations down the road if I ever wanted to make this adjustment. So, yeah. There's a little note there. And another valuable concept introduced is state management within variable simulations. Unlike standard scripts, simulations evolve based on a random sequence of human inputs. The code must manage variables carefully to preserve data integrity across turns. This experience shows how small oversights, such as forgetting to update an ace's flag or miscounting the deck's remaining cards, can disrupt the entire system's behavior. Holding edge cases is another concept used in this project. For example, an ace card cannot hold a single point value because doing so may cause hands to bust unfairly on the very first deal. Like 2 aces deal, that's a 22 if it was shown there, and that would be unfair. But additionally, the program had to handle invalid user text inputs to protect the execution loops. These requirements demonstrate how important complex conditional branching is to program stability. Now, we're on to challenges encountered during development. One of the biggest challenges in building this program involves the sequencing of the game evaluation logic. Blackjack contains layered casino rules, capturing the correct order in which events must occur, dealing cards, checking for natural 21s, evaluating user hits, checking for player busts, and running automated dealer paths. Some of my early drafts checked for dealer wins before running the ace point correction loop, which led to incorrect losses for me, the player. Another challenge was related to user interaction mechanics and structural code separation. Because the program collects text inputs directly from a command line, handling unexpected characters, like if the user were to accidentally type in JIT, like J-I-T instead of H-I-T, that was a constant headache. On to reflection and future extensions. So this Blackjack program serves as a foundational exercise to learn in a hands-on manner how to create a more cohesive program and see your work come together, kind of like baking. While the current command line interface is text-based, it sets up a solid framework for building advanced simulations, and these could include probability modeling, bankroll tracking layers, or full graphic interfaces. Expanding the program could also let me use machine learning models, or AI, to study long-term house edges across millions of simulated hands. So just like constantly getting data. And then going on to the conclusion. This project is a meaningful academic exercise in intermediate level programming, decision making, control logic, simulation, and state-based reasoning. The Blackjack program effectively captures the core mechanics of table gameplay while providing an expansive code framework that can be scaled up in future iterations. Its developmental life involved thorough planning, structural division, and attention to the many logic rules. Through the structural challenges previously talked about and the concepts learned, this program stands out as a functional, reliable program for future and deeper coding projects. So, thank you. Hopefully you weren't bored too terribly bad. Dang, 18 minutes. Ooh.